Hello, everyone. So good evening, and now it's 8 o'clock. So we are about to start today's discussion, the live discussion about AMC8 for this year that happened in the past 10 days. So here is the Zoom meeting. And so for the moment, I have muted everyone, but if you have any questions or comments, you can put it on chat. And after I finish my presentation, I will also allow people some time to ask questions. And given that this live session is also broadcast on YouTube, so maybe let's wait about a minute to make sure both channels are fine. Then we will officially start. So can I check with everyone that you could see my voice and also share the screen? And if you are a student, actually, I suggest you to log in the Zoom through the laptop so that later on when we discuss the problems, you could have a bigger screen so it's easy to see our explanations. All right. So now I'm going to start my explanation about AMC8. So AMC8 this year is already finished. And to get things started, so first I will give out a quick self-introduction. And from the participation list, I could see many friends. And just in case for those of you who don't know me, and my hometown is in Beijing, and so luckily, when I was a high school student, I could represent China to be in the International Mathematical Olympiad team. And, and in that year, it's 1994, and IMO was happened to be happened in Hong Kong, and I was lucky to get the full mark with the gold medal. And after many years, I came to Hong Kong to work in Hong Kong, and since 2016, I started to organize AMC in Hong Kong, Macau, and also in recent years in Japan. And we also, within the Asian region, we have close cooperation and discussion with people in mainland China, in Korea, as well as New Zealand, Australia. And in addition to that, since 2019, I think many of you know that we have introduced the mass Congress contest into Hong Kong. And so this is also one of the other competitions that I organize. And so this is the quick self-introduction. And today's topic would be AMC8. So I would also like to talk a little bit about the history of AMC8. I think all of you know that. So when we're talking about AMC, AMC stands for, it's also on the screen, American Mathematics Competition. And abbreviated as AMC. So 8 is stands for grade 8 or below. And of course, we probably you know the joke that in Shanghai, people say that AMC8 is for a math competition for year 8 or below. Yes, it's true that in mainland China, many primary school students attend AMC8. AMC8, that was not his original name. So for American mathematics competition, actually, there is one with a longer history, which is called uh, American High School Mathematics Examination, abbreviated as AHSME. And that competition was started in 1950 from New York City. And these both the old version, the old name of AMC8 as well as AHSME, they are all multiple choice kind of math contest. So when AMC8 was kind of like introduced in 1985, it was actually called American Junior and then HSME, High School Mathematics Examination. And later on, around 2000, it was changed into both competition turned into AMC8 and AMC10 was introduced as kind of really the junior high school, and then AMC12. So that would be the three competitions within the AMC. And you could see from I showed up the front cover of the first AMC8 as well as the first so AJHSME, and you could see that the first AMC8 problem was fairly easy, but nowadays the problems are getting harder and harder. And the next, and so for me, of course, now I'm involved in the organization of AMC8, but I was also the AMC8 participants. So when I was in middle school, and so that is back in 1990, I attended the AJHSME, the fifth AJHSME in China, and so that was a award certificate, and you could see, of course, everything is in Chinese. So you know that for the AMC, that it is kind of like a global competition since 30, 40 years ago. So now I think AMC was organized in more than 30 countries and regions. And next, and I'm going to talk about the problem design. Of course, at least for now, all the AMC competition problems are designed by human, normally by the math teachers and math professors. And for each AMC8, AMC10, and AMC12, there will be the problem kind of like editorial board. And so in this page, it shows the co-editor for AMC8, which are two professors in the US. And if I'm not wrong, actually uh, the gentleman now is already works in Amazon instead of a university. And for the problems, and so so basically there for each competition there is a group of people that are designing uh, the, the the problem set for a year. And the contributors definitely more than just the editorial board. And you could see that for these years AMC8, there are, if I count correctly, 16 or 18 people that are the problem proposers for the AMC8. And then after all the different people propose different problems, and then there will be a selection process happen. And so in the end, we select the best, the so-called the best problems. But here, when we're talking about the best problems, it doesn't mean that the problem has to be very difficult. I think the best problems would be they kind of like have a new setting, and but is kind is test the students' creativity because it's a new phase and you don't know which formula or which technique to use. But also it is not very hard. So that would be the best problem. And I think AMC was widely known. One of the very important reasons would be the high quality of the AMC problems. And in some local competitions, in many places, you could see that they will select AMC problems maybe as a prototype and change the number or whatever become their competition problems. And so that is how in general the AMC problems are designed. And actually the similar process for the mass congruent problems, because like in mass congruent, I'm going to attend the so-called annual meeting somewhere somewhere in the world in the place, and then we design the whole problem sets for the next year. And now we live here in a fast changing world, especially in the recent years. It will be about the AI, and actually besides AI and the internet and the information kind of like delivery or transformation becomes much faster than before, and that actually creates challenges for the AMC organizations. And you know that for AMC8, it is administered around the world with that as we see a 7 day period. And as long as there's one dishonest student or teacher that kind of like spread out the problems, then it could have the possibilities that it could be spread quite fast. And as I show in this page, although we have the very kind of nicely designed rules to kind of like to disqualify the cheating scores, to discourage people to cheat, and actually overall a old math competition is we should not take that any math competition too serious, because essentially that is actually for fun, right? And it's for kids, for students to improve their mathematical capacity. And but there's the so-called bad people existed, and I have to say, and especially that is a headache for our organizers in AMC. And although in the picture I show a shield that we want to protect the problem security as much as possible, but the challenge is quite big. So because of this, we are taking many measures to kind of make this competition as fair as possible. And one of the changes this year is we use a totally different new set of AMC problems in Asia. And of course, that problems needs to be designed. And so far for this year is actually the AMC8 problems that were tested in the regions that I'm responsible, Hong Kong, Macau, Japan, as well as for some other organizers like in Korea, in New Zealand, Australia, and mainland China. So we design more than one totally different set, which is totally different than what the standard version. And and in the end, and and it turns out, I think it's the it's I wouldn't say that there's any perfect solution, but it's definitely better than before. I did receive some feedback. See there are some students who kind of got the answers of the standard version not in a very good way and memorize the answer. And turns out that when they show up in the exam, it is totally useless. And and because of and uh, 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 and of course there are also other kind of like complaints and suggestions about, we have more than one side of problems. I think that is something that we have to gradually improve, and hopefully in the long run, we still could make AMC a very interesting and joyful event for students. So to preserve the reputation of this competition as well as to make it has educational function. I think it's a goal that all our organizers around the globe are trying to achieve. And so for this year, all the new problems are designed by, of course, by some people, math related, and including myself. And I have to see that all these people has a common feature that we all graduated from the School of Mathematical Sciences in Peking University. And uh, so now I'm going to talk about like how the problems is designed for the called the Asian version, the version that Hong Kong and Macau and is used, and uh, for to design a new set. And of course, the keys the best thing would be that the two sets, although the problems are totally different, they pretty much test the same kind of like uh, the same type of the contents, maybe have the same level of difficulty. And so in the end, although there's no way to achieve that, but the ideal case would be for students to attend to use either side, as long as there's no cheating, they pretty much get the same score. So that would be the ideal. It is our goal to try to seek when we design the new problem set. So that's why, so in each problem, when we design the new problem, we try to make it cover the same topic with the standard set so that the two problem set will look as much similar as possible, while for those who got the answer in a bad way can still not get benefit from it. And so now I'm going to go over a few problems and talking about how we design the kind of create the new problem. And also I will explain, I will talk about some useful like problem solving techniques so that today it is not only we are talking about some logistical things, but we only do some real mathematics. So in AMC8, we know that we need to finish the 25 problems in 40 minutes, and we only have 96 seconds for each problem. So it's very important that we we find clever method to solve a problem fairly fast. All right. So now we do the start of the math part. Okay, so first is the last question, which is the so-called supposedly to be the most difficult question. So the most difficult question in this problem is saying that they have a regular hexagon. And they have a equiangular hexagon and inside equilateral triangle. And so for these equilateral triangle, and what you could see that the side length is easy to see that it would be 6, right? And we have 2 here, 1 here. So 1 plus 3 plus 2, and that is 6. So the question is asking that within these equilateral triangle, how many kind of like these hexagons can be constructed? Actually, the idea for this problem, of course, you can draw it, but in order to master the structure, so the idea for the geometry problem, it is better that you understand how the figure is constructed. Yes, now this figure is given, but a way to understand and to think about the figure, how the figure is constructed would be when we have an equilateral triangle, if we cut out the 3 corners, and then we get a kind of like a required hexagon. So that's why the size of these uh, 3 corners that has been cut off, that is more important, or that is essential thing we need to count. Like here in this picture, it's related to a triple of numbers like 1, 2, 2, right? And this 1, 2, 2 can be also other numbers like 1, 1, 3, or maybe 2, 2, 2, and then that will correspond to different hexagrams. And so then that means this question essentially is actually to find out some numbers, to list out some numbers, list out three numbers, and with some property. So that is the key structure for that problem. So by that, because of that reason, for when we change this counting problem, so we actually don't use geometry, but we change it into the other way, which we change it into the question that is to ask if we express a two-digit number 58 as the sum of three numbers. So what would be the case? And of course, to 58 as to express 58 as the sum of the three numbers, there are many, many ways. So there are many, many ways. So we need to kind of like restrict each the numbers in this expression. And the way we think is we find out a restriction which says that all these numbers needs to contain a digit one, right? So these are the restrictions, and with restrictions, and you could see from the choices, and there are not that many ways to do it. So that is like how a problem is designed, and to try to kind of like similar or have some connection with the original set. And then for this type of problems, how to do it. So here I want to show the example. Like so nowadays, there will be so many different AI models, and among these AI models, and if you, as long as you throw a problem in, and for geometry, you can even throw a picture in, and then they will generate a solution for you. Of course, there's no guarantee that the solutions are 100% correct, but sometimes you will see that if you encounter difficult problems, unless you can put into the AI model and see if it helps you, or at least you could see from the solutions, and will give you some hint, right? So now let's see how the AI. So I put this into AI, into one AI model, and then this is the solution they generated. Okay, so they say that you could see that, and they first list out all the two-digit numbers that with contains digit one, and of course that would be including all the things that starting with 10 something, right? So that is one type. So it's 10 something. And then the other type would be something with the last digit is 1, so like 21, 31, so on. So there are two types of the numbers that we need to think, right? So this definitely is very important as a necessary analysis. And also you see that they consider what? They consider the smallest number. And they notice that the smallest number has to be at most 19, right? So that is a analysis they have, and then they start to do lots of caseworks because the smallest number is 19 and the smallest choice is 10, so they do 19, 18, 20, 17, and so on up to 10. So they do kind of like 10 cases to get the answer. But this is not the best solution. The best solution is what? The best solution is you see among the 10 something, right? If you add up 19, you add up 18, you add up 17, you add up these three numbers, 17 plus 18 plus 19, that is 54. It's too small. There's no way that you can fit in 58. So actually a better way to think would be you think what? You think about the largest number. The largest number by our analysis just now, we know that the largest number cannot be 19. So the next choice would be 21, right? So if this is 21, and then what's left would be you see it would be 37. So 37 happens to be 19 and 18. There will be no others. And then, so that would be the first case. The second case would be you try 31 and also you try 41. But you see, if you try 31, so the remaining one is 27, we do have some choices, 10 plus 17 and so on. But it's 41, then the remaining two numbers have a too small sum. There's no way that it can match. So essentially, there are two cases, and we quickly list. So this problem, I think, can be finished within 2 minutes. For this AI solution, yes, it turns out they do get the five solutions, list out all the five solutions carefully. And you may, for those of you, you may wonder why there's a dollar sign involved in the solution. It's because they all use the mass editing language LaTeX to know the solutions, and for all the AMC problems, no matter whether the original the US docs as well as the Asian docs we generate, it's all use LaTeX. So for those of you, if you are students and if you have free time, I do suggest you to learn LaTeX and know how to typeset the math formulas. Okay, so from this you see, from this solution, what I want to suggest you is the AI solutions nowadays they may not give you the best solution, but they can give you some hint, or at least they can trigger you to think something, stimulate you to think something, and then it still needs your creativity to get better solutions. Okay, so now let's see the next problem. The next problem would be problem 24. And in the original set, it is actually about the factorization in a factorial. And for that problem, I think it's not that difficult. What we'll need to do is just to use a little bit of calculation, but the essential thing to test in this problem is every number can be expressed as a bunch of prime, as a product of a bunch of prime factors. So that is the structure. So to mimic this structure, then we think, and then this comes up with this question, which we are still talking about the prime decomposition, but we consider the divisors. For 2026, it is not uh, it is the prime factorization because this year is 2026. It is better that we know the prime factorization of 2026, but this is not a very interesting one because it is 2 times 1013, and 1013 is a prime number. So because of this, so what we do is then I see uh, uh, probably we extend a little bit, right? Which then that comes this question, which we see that the large 20 to 2026 is a divisor of a larger number, which means this number is definitely contain 2026 as a factor, but there will be others. And for this quotient, and what this could be? And we know that for this quotient, because 2026 is the second largest divisor. The largest divisor is number itself. Because it's the second largest divisor, which means the other side has to be very small, right? So the other side is very small, so this has to be the smallest prime factor. And then for the smallest prime factor, but given that 2026 already has a 2 in it, so it has actually must be 2, right? So n actually has no choice, but it has to be 4052. And because if we list out the numbers, then it is easy to verify the choices one by one. So that's why we have to what we have to do is we have to ask a question here. That is a typical way of asking things, which to ask the sum of the digits, right? The sum of the digits, and then you add up together, you get 4 plus 5 plus 2, and you know that C is the correct answer. That is how a problem is modified. And so we try to modify the problem. Some problems after modification become harder, and some problem becomes easier. I think for this problem, you can see that it does not need too much calculations. Once you understand it, immediately you can get the result. That definitely takes less than 2 minutes. All right, so now next problem. So next problem is a geometry problem, and that geometry problem is in the standard version, they say that to calculate kind of the circumference of this band. This type of the question, I would say these problems is not as creative as the two problems we just discussed. These types of things appears in many in other computations before, as the key thing is you locate the the radius, and then through the radius and all the corner part actually form some arcs, and then you add up together, then it would be fine, right? So that's why for this problem we would not want to change to just change the, see there's a 5 circles, and maybe we squeeze in another circle, whatever, but we try to still find to test about the arc length, but to have a different structure. And that different structure is also here, it's kind of like 5 sides. It's part of a regular hexagon. So that's why we start with a regular hexagon, and we see if we draw 3 arcs and we form a curved triangle, can you find the perimeter of that? Which means essentially you only need to find the arc of each one, then that should be fine. And for this problem, it is also to test you whether you understand the basic facts about things related to equilateral triangle, right? For equilateral triangle, actually it is very important that you know what are the basic things, right? So for equilateral triangle, we know that if the side length is A, what would be its height? The height actually would be square root of 3 over 2A. And also, there's another area formula I hope every students remember, which would be square root of 3 over 4A square, right? So that is the some standard formula. So when we apply this standard formula, actually it's quite easy. And how to identify the radius? To identify the radius, we just connect AE, and you will see originally the line side length is 1. So that will be square root of 3 over 2. That is height. There's another square root of 3 over 2. So we know that the radius is square root of 3. And then what will be the central angle corresponding to each arc? That is also clear, right? It is has to be 90, 60 degree, right? Because here, without the curved triangle, we can construct an equilateral triangle in it. So you know this is 60 degrees, 60 degrees, 60 degrees, 360 degree would be 180. So now what would be the circumference? It is 180, it's just like 180 over 360 times 2 pi r, right? Pi r, this is square root of 3, and these two cancel out with half, so it's just square root of 3 pi, right? So, you know, for this, it's also fairly easy to get it if you know the basic formulas. That's the geometry problem. So the next problem, and it's called a statistic problem. What they say is, they say this is very nice design, they see we separate these 1 through 25, which is 5 square, into 5 groups of 5 numbers each, right? So in order to denote these situations, we could see, for me, I would like to draw the little dot. Okay, see, these are the 5 groups. Each group have 5 numbers. And then they consider what? They consider the median of the medians. The median of the medians means what? It means if here that is the median of each group, and along this group, you consider the median again, right? So that is the situation. Now, then that means what? That means the construction would be we have to make the median as small. The first 3 medians, right? So the first 3 medians should be, so these 3 medians should be as small as possible, then together with the numbers below it, so that you can really make it small, right? So how to make it small? Then that will be, you could see that will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually, which means we have to, so for the medians of the median, definitely it has to be the largest number within this region. So that's why the median of the median must be 9, right? And actually, if you have this construction, immediately you know that it has to be A9 is the correct answer, as this is already the smallest, right? So it's kind of like this construction, so which talks about the median. But if I just change this into 4 by 4, change into from 1 through 16, that's probably too hard, as the median becomes the average of the two numbers. If I just change 25 into 49, which is 7 square, probably it won't that interesting, right? And if you already solved this original problem before, then you can easily guess the other answer as well, right? And so that is the reason why. So gradually we in the process that we fight against cheating, we change from slightly modify some numbers to kind of like use new problem, because we want those who dishonestly get the problems and answers have no disadvantage, or have the advantage as small as possible. So then that means we have to design a problem about the media. And so after some thinking, after consulting with all the other the other computation problem that involves the media. So the key structure would be when you have the odd number of a set with the odd number of data. And what we'll do is the median is always the number in the middle. Now, so we design a case where there are only 3 numbers. So in many math contest problems, there are things with 5 numbers like this, one, or even with 7 numbers. And then if I give the condition about say the median is something, then of course you know that what is the middle number. So now this problem design is say, okay, so now if we changed it into change some values, then then the median change. Then the median change, and then you know that the number change cannot be the middle number, must be other numbers, right? So by that way, so we know that we have this problem. Like here, we also add up some average condition, which shows that this change is actually just means you add up a number by 6. When it becomes 32, so the other number must be 26. And then, so The other number is 26, 6, and so the thing that for the third largest number must be 64. So again, if you are familiar with this structure, then you also get it. And as I mentioned, that we have actually designed more than one set of problems as the computation period is quite long, and there's also the risk that the problem uh, was kind of like leaked, not through Milan, China, but like we see our regions. So that's why we have slightly different sets for people who take the computation at different days. And for example, for the next 25 problems, is the one in one of the sets that would be have similar structures with the previous one, but it's only that we consider two sets and the difference of the two medians to make it a probability problem. That is how this problem was modified. Okay, so that's problem 22. And for problem 11, that is a probability problem. And that probability problem is also it's about a spider walking along a web. So that is the structure. It is a spider walking along the web. There are some choices at each kind of intersection, and then they will go by certain kind of probability, and we calculate something. And so that for that, in order to change, essentially we change the web. So we change the web from a 5 star into also we need to change something not too complicated. So we change this from a 5 star into a square with its center. And so originally we have the so-called the inner points and the outer points because so these would be the outer points, and then there's 5 inner points. While here we can distinguish with the vertex points as well as the center point. So everything else is the same. So that's why for those, if you really understand the probability and you can solve it. And for those who just memorize the answer to the original problem, you have no use at all, right? So that is how we did change structure. All right. So now next would be the enumeration problem. So they say that this problem 20 is actually means in the US version it means if we want to express 8 as the sum of some numbers, and so here each number is either 1 or 3, and we do count the orders. How many possibilities are there? So it is to express as a sum. And we want to change it. So one thing we do is actually we use AI and we put the problem, ask AI, I want to modify these problems. Could you give some suggestions? And of course, most of the suggestions that AI give are just change some numbers, not so good. And but these but this one, the AI gives a relatively good one. What they say is they change the number. So originally it would be you use a bunch of 1, 3 to form a sum of 8. But here they change it into the question of like Robert climbed the stairs, but essentially mathematical. Mathematical setting is exactly the same. But here they say that they change 10 into the sum of some numbers, but each number is 2 or 3. So this is one thing, just number change. But they add that because 10 is a bigger number, they add an additional condition. See that they cannot take 2, 3 steps in a row. So the 3 and 3 cannot be next to each other. And then in one of the versions, we see that 2 stacks cannot be in a row. So 2 and 2 cannot be stacked to each other. So that is we change it slightly different, and but all the essential method is the same. So you have to list and organize, list things in an organized way. Okay, that's how we modify problem 20. Now next, let's see problem 19. So problem 19 has a nice picture. It is about a journey that they have different directions between uh, between a person and his dog, right? The structure itself is that. So which means I need to also design a journey problem, and it's better to have kind of nice picture. So also in these problems, what you see that is the dog is actually kind of change the direction. So in a way that there is a kind of like two-person travel, essential structure is two-person travel in two different directions. And we just take this kind of structure and we design and we have some settings and then we get this problem. And for this problem, so nowadays becomes as the AI is so powerful, so if I threw the description into the AI model, then they can generate these two people for me. One is this kind of like running, and then the other person is riding a bicycle. And for the names, because that other names appeared in the oh, in a problem of the original version. So we just use the names, try to set up the connection between the two versions. And of course, everyone understand why the town's name are named by A, M, and C, right? Okay, so that's how we change into a different journey problem. But of course, essentially, we need to use the relationship that the distance equals time times the speed. Now, next. Next is you see that question is about kind of like a number theory. They see that they want to express 60 as a sum of some consecutive odd positive integers. And I see you probably just say that we already have a question which is to express 8 as the sum of something, right? And now this question is again 60 as a sum of something. So there's a little bit of the repetition about the structure. And not to see that in problem 25, we already changed it into also the kind of like the splitting sum of 58. So that's why for this problem, we need to change it into some other kind of like type so that to make it more interesting. So what we change is then we are thinking about that the divisibility hasn't been tested really in the problem or when we're dealing with problem 24 in the original version they kind of like have the feeling of divisibility. So that's why it comes to this problem. And in this problem, what they say is that you randomly select an undigit positive integer. The probability that this integer is divisible by n is 1 over n. So this sentence looks very long. There are lots of n's involved in it. But if you think in other way, then that you feel that this statement actually sounds natural because if you have any unconsecutive integers, right? Because when they divided by n, they will have n different remainders. So the probability that the number is divisible by n should be exactly 1 over n, right? So in that sense, you will see, okay, so then normally it would be that. But the thing it would be only among all the n-digit numbers, whether you can really cut it into a kind of like the different periods where each period contains n numbers, right? So that is the thing. And by that thing, so we would see that this means the question is changed into the number of n-digit numbers. How many n-digit numbers are there? So it's actually is because the number of n-digit numbers starting from, you see, 1, 0, 0, 0, 0, and up to 9, 9, 9, 9, right? So and which is which is 10. The next number is n digits, right? So the next number would be just 1 times 10 to the power of n, right? Which is followed by n zeros. And so here it is 10 to the power of n minus 1. Then how many digits are there? It's easy to count. This is just uh, 10 to n to the power of n minus 1. So the number of n-digit numbers is just 9 times 10 to the power of n minus 1. And we need to make this divisible by n. So we make this integer, right? And now, which means n needs to contain kind of like the prime factor 9 to 5, right? But no others, right? So 9 to 5 are good ones. And from this here, this is good because this is 3 times 32. So that is good. In the other version, we use 72 as a good one, which is 9 times 8. So that question is, once you do a simple counting, then you should be able to get it. Yes, generally speaking, I think the general feedback is this problem is quite difficult. All right. So next problem. So next problem is a problem that I feel the best among all the original version. Because that problem, they have a very natural, it's easy, the condition is easy to understand, but it's kind of like a totally new setting related to an old type of problem, which is arrangement, right? So you have 4 people arranged in a row, everyone knows altogether how many ways are there for factorial. But they are questions that they are asking about a rearrangement of the setting so that the condition is that everyone's no longer seated next to any of the same people. So this is a very nice design. And also 4 is a very small number because for the middle number, for the middleman, right? Originally it has 2 neighbors. So in the next sitting, there's no choice, but he has to be next to the first person. And also in this case, because there's only 1 neighbor, the only possibility would be they have to be on the corner seat, on the corner seat, right? And so that question is not difficult, but it's really nice, right? So to change such a problem is a little bit challenging because you cannot change 4 into 5. Then such kind of restriction become much less. And but I think about a mathematical way, which we know that somehow, topologically speaking, so here we are dealing with a line. The line, if we add up the infinity points, it is the same as a circle. So that's why instead of arranging the 4 people in a line, so we design a problem that we arrange 5 people in a circle. And also the problems actually was designed during the Christmas and New Year period. So that's why we changed the 2 setting, the original setting called Christmas party and the new setting called New Year party. Nowadays, although I'm not good at drawing at all, but AI can help us do it. And we request AI to show that these 5 different people, they do have 5 different faces so that they are different. And we also use a table to show that these 5 positions are different, right? but the argument is similar, right? Originally, we have two neighbors, and now it has to be changed into the other neighbor, and the way to connect them is actually will form a kind of like a 5 star. So that's problem 17. And so we are going to go a little bit quick. So for this problem, it's about a classical probability problem that we are talking about the numbers that whether you can use some numbers to divisible by 4 and by only using the even digits. So what do I do is then we're still thinking about divisible by 4, but probably we change it to make a dice problem. So we throw out two dice and we ask for the two numbers. So normally for the two standard dice problem, if you have already done all the historical AMC problems, you would know that they were very common. However, we need to have some new design, new feature. So that's why it comes to the condition that so we want the two digits row that can be arranged to form a two-digit number divisible by 4, which means if you roll out a 2 and 5, right? So although 25 is not a multiple of 4, but 52 is divisible by 4. Then in that sense, both 2 and 5 and 5 and 2 should be included in the calculation as a good case, right? So that is kind of the small change. So we want to try to make the problem has a new setting. And it turns out that this problem has very low correction ratio, probably because of this. Okay, so the original problem 15 is about a three-dimensional geometry problem. And when we do it, we are still thinking about the 3D problem. But that problem, the design is a little bit complicated, although the construction is fairly easy. So you just form a 2 by 2 with all the gray cells inside, can make it purely white one. And so what I'm thinking is we are just using still the cubes, but we just use the cubes to expose to have the smallest surface area. And for the smallest surface area, so that is one design. The other design is, so here we are using 7. So why we are using 7 identical cubes giving? Because 7 is exactly 8 minus 1. So 8 means what? 8 means we can form a 2 by 2 by 2 cube. So now here it is 1 less. But for the 1 less one, what you just need to do is you can just remove a corner. But when you remove a corner, 3 faces disappeared and 3 new faces arise. So the surface area does not change. So that is the best design. Again, similar as the previous, the original question, as long as you get the best design, you don't need to worry, it must be the smallest one. It's choice A. Okay, so now these are the few problems I do. And I think time is limited, and probably I also prepare some other things, but I'm going to skip. And now in the round the clock, so I'm going to talk about the last topic, and which is the topic that many people will quite want to know, which is what will be the statistics. So here is the problem difficulty. And you could see that relatively speaking, the first 10 problems are relatively easy. They have the correction ratio like above 60%. And so there are some problems that are fairly among the problem 10, 11 to 20. There are some quite difficult problems like here. But generally speaking, most of the problems have a correction ratio is about 30, 40%. And of course, as these and these, that there's in the last few problems, it's a little bit to my surprise because as long as as long as you can guess, because AMC8, there's no penalty for any answer, the correction ratio should be at least 20%. But probably because the time is very limited, we could see that still some students leave the last few problems empty. Yes, some students do guess, see every guess A or C or E or whatever. Yes, but that's why. So we still have some problems that with the correction ratio below 20 because there are some empty answers. So the law of large numbers does not really form. And also, to my observation is for those who always select the same answer for the last few questions, the average correction ratio is also less than 20%. All right, so the next page, I know that would be the page that many people, participants today, care about, and which is a statistic about the score distribution. And so here are the regions that we manage. And in these six regions, we list out the score distribution for each score. And we don't have that many scores, there are only 26 choices. And then, and also about the most number of participants among these six regions are from Hong Kong. I think in Hong Kong we have around 2,000 participants, and all the other five regions has less than 1,000 participants. And so the overall score distribution would be like that, which means, yes, we do have some students that get the full score. And I think getting the full score is really an honor. And of course, as I hope, we do have the design so that those who get the full scores are all by their own capacity. So while I'm preparing for these PowerPoint. I checked the PowerPoint 6 years ago that during the COVID period, and so there's a AMC8 which was managed and purely online. And in that AMC8, the full score and 24, there's one person with full score, there's one person with 24, and two people with 22, and no person get 23 in Hong Kong. And among these four people, top four people, three people later on becomes the IMO team numbers for Hong Kong. Right? And and so top 1%, by that, it would be mean 23 as a cutoff. And top 5% would be mean 19, because up to 20 is still less than 5%. And then starting from this year, we also have two new words which called top 10% and top 25%. That the corresponding cutoff would be 18 and 15. And so that would be the estimated cutoff. Of course, this year we have a new situation because we are using different sides of the problems. So we need certain kind of coordination to make sure whatever the certificate we distribute is to the best, to be as fair as possible. And I do receive the comments from some students saying that this year's AMC8 problem probably too difficult, so that their performance is even worse than last year. We did some preliminary analysis, it's not fully complete, but we could see that, yes, it's true that for most of the students who take the AMC8 in the in the in the past uh, in this year versus last year, the average is about the same, right? So given that the average is about the same, that is something would be abnormal for the two problem sides with the same difficulty level, right? So which means definitely this year's AMC8 problems are difficult because we have a totally new set. And so by this means, if we check the top 1% and top 5% scores, this is exactly the same with the cutoff last year. As when we determine the cutoff, when there's only one set, the way to do it is we make it based on the statistics of domestic US and Canada. So I think in the past, it's already the case in Hong Kong that there will be more than 1% of students, 1% of participants that got DHR, and there are more than 5% of the participants that got HR. So the average capacity, the average student pool for the AMC8 participants should be slightly better than those in the US. So in that way, so probably to make the things consistent, we should adjust the cutoff score slightly below the actual to make it consistent. So that is something that we are going to discuss with MAA and finally make the determination when or the cutoff score in the US was announced. Okay, so that's the score part. So I have my final word. So AMC8 is famous and very important, but actually along the way, we have many other competitions. So to me, I would think each competition is kind of physical check up, right? So if you got good in a competition, that's nice. It shows your capacity. If for some reason you didn't perform well in one competition, that's natural, and you can try it next. For example, related to like grade 7, 8, along the year. So in the next month, now it's already February 1st. In the next month, we are going to have our Hong Kong Mass Congress contest, which covers all grades. And that contest has more than probably we will have more than one participant in each grade. So that is also someone that you can measure your percentage. And after that, we also have some Canadian competitions for different groups that you can attend in April and May. And then coming next in the fall semester, and for the AMC equivalent in Canada, which are all the competition named by the animals, like the Canada J competition, which abbreviated as CJMC, will happen in November. So along the year, actually, there are many competitions you can participate, and then through these competitions, of course, different competitions have different participation too, but the different populations, but still you can get some ideas on how good is your mathematical capacity, and also you can build up your experience, you kind of like doing this competition, which like you need to have a very peaceful mind within a fixed period of time. Okay, so that I think that's all I want to say. And if you want to get the detailed statistics and or you have any questions, you can contact me or the assistant through the contact method here. Also, I just mute all while giving the lectures. So now I'm just going to, uh, I think I already uh, unmute everyone. I think now you can, if you have questions, you can unmute yourself. And also if you have questions, you can put it on chat and I can quickly answer. Are there any questions? Yes, and we are going to release the modified set of problems after everything is settled down and all the score all the scores has been graded, so that students can review and learn from it. Are there any other questions? I think the average score is around half, just like 12, 13, and from okay, so it seems there's no other questions, and I think that we are going to end here, and feel free to contact us in case you need anything, and I hope it will be I think it will be a wonderful event for everyone. Yes, some people ask whether we have the average, which is the average by the grade. Yes, we are editing on that. We will try to create some more data so that you can have a comparison. In this case, you can just add us our contact method, and once the data is ready, so we are going to send it to you. Okay, so now if there's no other questions, we are going to end the meeting here. And thanks for everyone's support in the AMC event. And our work is we want to try to create some meaningful mathematical actual curriculum so that students can benefit in this kind of fastly changing AI world. Okay, then that's it for now. Bye bye.